Alright, so this is going to be sample problem 16.7, freezing and boiling point of an electrolyte solution. So freezing and boiling points with an electrolyte. Okay, so it tells us determine the freezing and boiling point of a solution prepared by dissolving 82.20 grams of calcium chloride, okay, in 400 grams of water. Alright, so we know that the mass of the solute of the calcium chloride is 82.20 grams. We know that the molar mass, if we look at the periodic table and add everything up, the molar mass of calcium chloride is 110.98 grams per mole. We can also find the mass of H2O, because that's given to us as well. That's 400 grams. We know that the Kf, alright, so remember the Kf is the molal freezing point depression constant. Okay, so the Kf of H2O is 1.8, well, negative 1.86 degrees Celsius per molality. And remember, that's a italicized M, so that's molality. And then the Kb, which is the molal boiling point elevation constant. Okay, so the Kb for H2O is 0.512 degrees Celsius per molality. Okay, and we know that calcium chloride dissociates into 3 ions. Okay, so what we need to find is the Tf, the new freezing point, and the Tb, the new boiling point in Celsius. Okay, so the first thing we're going to do is calculate the moles of calcium chloride. All right, so we have a mass of 82.20 grams of calcium chloride. We're going to multiply that by the molar mass. Now we've got grams on top, so we need grams on bottom, and we need moles on top. That way grams cancel, and we'll be left with moles. So the molar mass is 110.98 grams per 1 mole. We multiply that out and divide, and we're going to get 0.7407 moles of calcium chloride. Okay, and this result is then used to calculate the molality. So now that we know how many moles, we can divide by the mass of the solvent, in this case H2O, and we're going to then calculate the molality. Now, remember up here our mass was given to us in 400 grams, but molality has to be in kilograms. So we need to convert this, and the way you do that, if you don't remember, is you're going to say 400 grams over 1 times 1,000 grams per 1 kilogram. So basically you're dividing by 1,000, so that'd be 0.400 kilograms of H2O. Okay? Now, so we're going to take the moles that we just calculated. Okay, and I'm going to move my sheet up. All right, so we're going to say 0.7407 moles of calcium chloride divided by 0.400 kilograms of H2O equals 1.85 molality of calcium chloride, or molal. That's the word. So when we talk about molarity, then we talk about the molar mass, or the molar situation. Molality, we would say this was 1.85 molal calcium chloride. All right. All right. Now that we have that, we can plug into our equation that we used previously, and we're going to say the change in temperature, the freezing temperature, is equal to the freezing point depression constant times the molality times 3, because there are 3 ions, 1 calcium ion and 2 chlorine ions. Okay, and so then we're going to multiply that out, and we're going to say negative 1.86 degrees Celsius per molality, or molal, times 1.85 molal times 3 equals, all right, so we're going to look at this. Molality is going to cancel out, and we're going to be left with just degrees Celsius, which is what we wanted. Okay, so we're going to multiply negative 1.86 times 1.85 times 3, and we're going to get negative 10.3 degrees Celsius. Okay, so that means that TF, the new freezing point, would be negative 10.3 degrees Celsius. So that's the new freezing point of H2O once we added the calcium chloride. All right, now we're going to basically do the same thing to find the new boiling point. All right, so we're going to say the change in freezing or boiling point, okay, is equal to the boiling point elevation constant times the molality times 3, because once again we have 3 ions. We have the calcium ion, and we have a chlorine ion, and then we have another chlorine ion. Okay, so we have 3 ions, and so we're going to substitute in, and we've got 0.512 degrees Celsius per molality, or molal, times 1.85 molality over 1 times 3, all right, equals 2.84 degrees Celsius. Because again, molal is going to cancel out. That leaves us with degrees Celsius. All right, so that means now the boiling point of water, remember, the boiling point of water is 100 degrees to start with. So then what we're going to do is we're going to take the starting boiling point, 100 degrees Celsius, okay, plus the 2.84 degrees Celsius. All right, so that means the new boiling point, the TB, is going to equal 102.84 degrees Celsius. All right, we did the same thing here, except we did it kind of automatically because the freezing point of water is 0. So 0 minus 10.3 is going to be negative 10.3. Okay, so that's how we did that. Okay. And so since the normal boiling point of water is 100 degrees Celsius, the calculated result for delta TB must be added to 100 to find the new boiling point. All right, so that was 16.7. All right, so this is 16.8. So this is molar mass from the freezing point depression. So basically we're going to be given how much the freezing point was lowered, And we have to figure out the molar mass that was added to it. Okay? So we have 38.7 grams of a non-electrolyte dissolved into 218 grams of water. The freezing point is measured at negative 5.53 degrees Celsius. So the new freezing point is going to be negative 5.53 degrees Celsius. Okay? We want to find the molar mass. So we know that the change in temperature, or freezing temperature, is equal to negative 5.53 degrees Celsius. We know the mass of the H2O, sorry about that, is 218 grams. We know we're going to need kilograms for molality, so we're going to go ahead and change that to 0.218 kilograms. Okay. We know the mass of the solute. We don't know what it is, but we know the mass of the solute is 38.7 grams. All right? And we know that the freezing depression constant of H2O is negative 1.86 degrees Celsius per molal. All right? What we need to find is the molar mass of the solute. Okay? And that will be in grams per mole. Alright, so that's what we got to find. So we know we're going to use the freezing point depression to calculate the molality of the solution. Alright, so we're going to take our equation and rearrange it so that we have the molality is equal to the change in freezing point divided by the freezing point depression constant. So we're going to say negative 5.53 degrees Celsius divided by negative 1.86 degrees Celsius per molality. All right. So what's going to happen is mathematically, this is a fraction divided into a fraction. So really what we're going to have is negative 5.53 degrees Celsius over 1 times the reciprocal of this. So we're going to have molality, sorry, that should be slanty, over negative 1.6 degrees Celsius. This means our degrees Celsius cancel out and we'll be left with molal, which is what we want. And so then we get 2.97 molal. All right. Then we're going to use the molality equation to calculate the moles of the solute. Okay. So we know that the mole of the solute is equal to the molality times the kilograms of H2O. Okay, so that's going to be 2.97, we just calculated that, okay, times 0.218 kilograms equals 0.648 moles. Okay, now remember molality, if we could rewrite that and we could say 2.97 moles per kilogram. Sorry, my brain stopped working for a second. Okay, and so then when we multiply it, wait, that doesn't work. Oh, yes, it does. Never mind. 0.218 kilogram over 1. Kilograms cancel out, and we're left with moles. Okay? And then we'd get the 0.648 mole. All right? So this is just me showing you how this, how we got to moles. Molarity is moles over kilograms of the, in this case, H2O. But and that's H2O. So those cancel out and you're left with moles. All right, next step. We're going to divide the grams of the solute by the moles to determine the molar mass. All right, so we know we have 38.7 grams, okay, of the solute. We don't know what it is, but we know how much we have. And we know that it's 0.648 moles, okay? So we divide that and we get 59.7 grams per mole, okay? So again, grams per mole. All right, so that's the molar mass. All right. Knowing the molar mass is an important step in determining the identity of an unknown substance. A similar problem could be done with the change in boiling point. All right, so you would just have delta TB if you were doing boiling point, and you could work it out pretty much the same way. All right. So this is lesson 16.4 now. We're doing sample problem 16.9, which is writing and balancing net ionic equations. All right. So we have a problem. When aqueous solutions of copper 2 chloride and potassium phosphate are mixed, a precipitate, remember a precipitate is not soluble, all right, in the solvent. A precipitate of copper 2 phosphate is formed. Write a balanced net ionic equation for this reaction. Okay, so we're going to write and balance the molecular equation first, making sure the formulas are correct. All right, so they give us a word problem. So it says things like aqueous copper 2 chloride. So we know that the copper 2 is a 2 plus. We know that chlorine is a 1 minus. So that means I have to have 2 chlorines, two negatives to balance out this 2 plus. So CuCl2 aqueous is mixed or added to when aqueous solutions of copper 2 chloride and potassium phosphate are mixed. So next we have potassium phosphate. And remember, phosphates are a polyatomic ion. All right. So phosphate is down here. Hopefully you can see it in the video, but it's PO4 3 minus. All right. So potassium phosphate would be K, which is a 1 plus, and PO4, which is a 3 minus. Okay. So that means we need 3 potassiums to balance out the 1 phosphate. And that's also aqueous. Okay? And they produce a precipitate of copper 2 phosphate. So again, copper is 2 plus, and phosphate, which is a 3 minus. Now these do not add up to 0, so that means I'm going to need 3 coppers, because 3 times 2 is 6, and I'm going to need 2 phosphates, because 2 times 3 is 6. And so that would equal out to 0. But it says this is a precipitate, so we know that it is a solid. Okay. Write a balanced net ionic equation. So that took care of the copper and the phosphate. All right. So what happened to the chlorine and the potassium? Well, most likely they could form KCl. And we could look at our solubility rules and see that that would be aqueous. Okay, potassium is a 1 plus and chlorine is a 1 minus, so that's the problem there. All right, if we look at the solubility rules, all chlorides, bromides, iodides, except silver, lead, and mercury are soluble in water. So since this is a chloride, it is soluble, so it would be aqueous. Okay. Now, then write the ionic equation showing all the aqueous substances as ions. Well, we have to balance it first. I'm sorry, it's not balanced. All right, I have 1 copper here and I have 3 coppers here, so it's definitely not balanced. So we're going to CuClK and PO4. All right, I have 1 copper, 2 chlorines, 3 potassiums, 1 phosphate. I have 3 coppers, 1 chlorine. I have 1 potassium and 2 phosphates. Okay, so, well, I'm going to put a 3 here. That gives me 3 phosphates, or 3 potassiums and 3 chlorines. All right, but then I'm going to need more chlorines on the other side. So the lowest common multiple of 2 and 3 is 6. So I'm going to change this to 6. I'm going to put a 3 here. That gives me 3 coppers, 6 chlorines, and if I put a 2 here, that gives me 6 potassiums and 2 phosphates. 3, 3, 6, 6, 6, 6, 2, 2. So that is balanced. Okay? Now, so what we do with that balanced equation, we have to write that ionic equation. All right? So I'm going to start way over here. Hopefully you can see. All right? So we've got 3 copper plus 3 Cl2. Well, I'm going to put a 6 there because they would be individual ions, so that makes sense. So we have 3 individual copper ions. Once these dissociate in solution, they're going to be individual ions. So these chlorines are going to also dissociate and be individual chlorine ions. So we have a total of 6 chlorine ions plus 6 potassium ions plus 2 PO4 3 minus ions, and they produce 6 potassium ions plus 6 chlorine ions plus these don't dissociate, so all right, and so then we're going to have plus Cu3PO4. But Mr. Furlow, why isn't that separated? Because it's a solid. It's insoluble, so it's not going to form ions in solution. Okay? So we balanced the equation. We turned everything we could into ions. We carried over the coefficients. Now we have to eliminate the spectator ions. So a spectator, oh, you know what I should have included? Aqueous, 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 and that's a solid. All right, now, so the spectator ions are going to be the same on both sides. Now, copper and phosphate are solid over here, so that means they are not spectators. So we're going to keep copper, we're going to keep phosphate, and we're going to keep copper phosphate. If we look at chlorine, it's aqueous here and it's aqueous here. So that is a spectator ion. If we look at potassium, it's aqueous on both sides. So that is a spectator ion. So our net equation, so this is the balanced equation, this is the ionic equation, or ion equation, and then we have the net ionic equation. Okay, so that is just going to be 3 copper 2 plus ions, aqueous, plus 2 phosphate ions, also aqueous, produce copper 3 phosphates. Oops, that 2 should be outside the parentheses. And that is a solid. All right. There you go. So we finished the molecular equation, we wrote the ionic equation, and then we wrote the net ionic equation. This would be the final answer, but the way this problem is worded, you'd have to show it all to get full credit. For a precipitation reaction, the net ionic equation always shows the two ions that come together to form the precipitate. That's these two. Okay. The equation is balanced by mass and by charge. Okay. So, if we talk about the charge, we have 6 positives here, we have 6 positives here, we have 6 negatives, we have 6 negatives here. So it all balances out. All right. Lastly, a little bit about your reference tables. Okay. You have the solubility rules here. Now these are abbreviated compared to your textbook. Textbook goes a little bit farther, but these are the most common ones you would need. Also, when predicting whether or not a reaction will occur, you're going to use the activity series. Okay. Don't forget about your polyatomic ion list. When something says it's like calcium hypochlorate. Well, what's hypochlorate? Well, it's right here on your reference table. Okay. All right. I'll see you in class.